Welcome back. In this video we're going to look at magnetic fields and how it relates to gang signs in physics. So the key concepts for today are looking at the concept around magnetic fields being associated with moving charges, looking at this concept of a solenoid being created by a current carrying conductor, and looking at how we represent magnetic field lines in terms of their strength, their direction, and things like that. The key learning outcome for today's video is to sketch and or interpret magnetic field lines produced by an electric current flowing in a straight conductor, a loop, and a solenoid. To set the scene, we have known about magnetism for quite a long time, and we suspect as early as 200 BC when some of the earliest compasses were used. Back then it was discovered that lodestones always pointed in the same direction, which happened to be towards the North Pole of Earth, and this was used for navigational assistance. It wasn't until 2 centuries ago that it was discovered that magnetism was actually related to electricity. And the key piece that we now understand is that electric currents generate magnetic fields. A magnetic field is a vector representation of the influence around a magnet, and therefore it should be defined in terms of a magnitude and a direction. So if we consider this direction problem, it's easy to say that if we have something like a magnet, the field lines go from north to south. But if we're now talking about electric current, we can't see or easily identify a north and south. So how do we define what the direction is that those field lines are traveling? The field lines are lines of force. So this means that the direction of the field line is the direction of the force. In the case of gravity, take our apple, which is just representing a mass. We said that the force and the direction of that force is the direction the object is pulled. So in gravity, it's always towards the center of the earth or down. In the electric field, we said the direction of the field line is defined as placing a positive test charge in the field and looking at the force that's exerted on it. And that direction of the force on the positive test charge is therefore the definition of the direction. In magnetic fields, we say it's the direction of the force on the north pole of the magnet, if it's placed in that point. And we use this word magnetic dipole, and a magnetic dipole really just means an object with 2 poles. So a bar magnet or a standard compass needle. If we want to investigate the direction of the field, we place a small compass needle in that field, and the needle aligns itself with the field, with the north following the field line direction. So the magnitude is the strength of the magnetic field, and this is represented by the number of field lines crossing a unit area perpendicular to the field. Very similar definition to what we saw with electric field lines. More lines means we have a stronger field, less lines means we have a weaker field. The unit for the magnetic field strength is Tesla. So the magnitude, how big the field strength is, capital T for Tesla is the symbol, is the unit, and the symbol that we're using to denote a magnetic field is a bold B to denote that it's a vector. So in electric circuits or in electric fields, we said E was the symbol. Now in magnetic fields, we have B as the symbol as well. So to look at that pictorial representation, if we were to place this little ring, which represents our sort of perpendicular unit area, here we can see that we've got quite a large number of lines that are passing through. This means at this point closer to the poles of the magnet, your magnetic field is much stronger. If we move further out over here, with the same sized ring, you can see we probably only catch 1, maybe 2 of these field lines, which tells us that it's much weaker out to the sides there. And you can see if we zoom in on these 2 cases, this is our weak field with only a few lines, and this is our much stronger field with lots of lines traveling through it. Now if we consider the Earth's magnetic field, note the direction is from the South Pole to the North Pole. But remember we just said that the direction of a magnetic field at any point is the direction of the force on the North Pole of a compass needle placed in that point. If you look at a compass needle near the surface of the Earth, it points towards the North Pole of Earth. Therefore, the North Pole of a compass needle and the North Pole of Earth are actually 2 different things. Given that the North Pole of a compass needle is that pole which points towards the North Pole of Earth, therefore the North Pole of Earth is attracting the North Pole of the needle, and that means it's effectively the South Pole to have that attraction in the first place. So what we know as the North Pole on Earth is actually the magnetic South Pole of Earth. In 1819, Hans Christian Ørsted, a Danish physicist, showed that a current-carrying conductor produced a magnetic field. Essentially, this means we can make magnets and magnetic fields purely with charges and current. The magnetic field that surrounds a straight current-carrying conductor can be represented using the field lines that form concentric circles around the conductor. These magnetic field lines become further apart, which signifies a weaker magnetic field, as that distance from the conductor increases. So we can see in our two pictures here, we've got a current traveling up. So this is our electricity running through a wire, for example, and it's going to create a circular magnetic field around the wire that as we get further and further out, the distance between those lines, those circles, gets bigger, which means the field gets weaker. In this case, we can see exactly the same thing, but the current is traveling down, and you might notice that the direction of those circles has changed, and we'll talk about why and how we do that. This links us to the right-hand rule. So often sometimes known as our physics gang sign. You'll see this all the time. I guarantee when we start doing tests and exams, there will be a bunch of students that'll pull out the right-hand rule and they'll be trying to orient things, and it's really great to watch. So we're going to talk about what the right-hand rule is and how we use this marvelous gang sign in physics. The right-hand rule uses your thumb to point in the direction of the current and your fingers to wrap around the object, showing the direction of the magnetic field. So if we looked at that example from the previous slide, I said that in one case the direction was going clockwise and the other was going anti-clockwise. And we can test this with our thumb. So if we have the current traveling up, as shown in the picture, our fingers curl around the wire, and our finger curl represents the direction of the magnetic field. So we can see it creates that anti-clockwise direction in this case. Look at these two examples we've got here. Which of these is incorrect? So which of these doesn't work using our right-hand rule? Hopefully you said the one on the right. If you use your right-hand rule, the thumb is traveling towards the left of the screen. Therefore, your fingers should curl in a anti-clockwise direction. That is not what the direction of the field lines that are drawn is showing. So therefore, that one is incorrect. It's actually the left-hand one. So some of the conventions that we use when we draw magnetic field lines. Think of the lines and the representation just like an arrow. If you had an arrow coming out of the page, it would look a little bit like this. You would see the point of the arrow piercing the page first, and it would sort of create this circle with a dot effect, or even just a dot sometimes. If, however, the arrow was going into the page, you would see the feathers of the back of the arrow, so you would see a cross that looks a bit like this. And this is the convention that we use when we draw magnetic field lines to show that they're going into a page or out of a page. It's easy enough to draw them if they're going left to right, up to down, because we can just draw lines with arrows. But this is a three-dimensional world, so we need to know how do we draw a field that's going into a page, into the screen, or out of the screen. And this is the notation that we use. So here we've got some examples. Using this representation, identify which of these is incorrect using the right-hand rule. Hopefully you said the right-hand one, and we can test this with the right-hand rule. So if the current in this case is coming out of the page, then we use our thumb to represent the direction. It's coming out of the page. Our fingers would curl around it, and therefore we would expect on the screen to have that anti-clockwise direction, which we see on the left. Now if we consider the magnetic field of a current loop, consider a loop of wire in which current is flowing around. So it's going around and round in circles in a loop. If you were to grasp the loop with your thumb in the direction of the current, and your curled fingers would then if you were to grasp the loop with your thumb pointing in the direction of the current, your curled fingers would indicate the direction of the field within that loop. This is another application of the right-hand curl rule. So just like we saw before for a straight wire, our thumb points in the direction of the current, our fingers curl around the wire, and that is the direction of the magnetic field. Now if we've got a loop, we follow the same process, but at any point our thumb points in the direction, our fingers curl around the loop, and that is the direction of the field. The field through the loop is actually approximately uniform. So similar to what we saw between parallel plates in electric circuits, within the loop, the field is roughly uniform there. Given that all of the field lines are closer together than the field lines outside, This tells us that the magnetic field inside a loop is stronger than the magnetic field outside a loop. And one thing you might notice is that no matter whereabouts in the loop you go, the direction is always in the same orientation. It's always pointing towards the left. So if we were to place our magnetically charged object in there, it would be propelled through to the left. And this leads into a great application of the current carrying loop. So if we've got a range of different applications or different representations, I should say here, you can see different kinds of loops. Here we've got electric current coming around, traveling around the loop. Here it comes up, goes around and comes back in. And you can see here we're using our representation. So this is the direction of our current. If you were to do that, you would see, using the right hand rule, the fingers are curling around. Therefore, the current is coming out of the page on the outside, curving over the loop and then going into the page on the inside. And that's why we see all of our crosses on the inside. It's the tail of the arrow. And on the outside, we see the points, which are the dots as it's coming out of the page. Same thing we can see here if we reorientate it to a different angle. We can see here is our current, and this is the direction of the magnetic fields going through. So next lesson, we're going to look at what are some key applications for this, being the solenoid for one, and even other applications such as the railgun for a military application of the magnetic fields. So stay tuned. I'll see you next lesson.